All right, let's get right into it. Welcome to this explainer for your first year IT Data Communication Networks module. Today, we are laser focused on Lesson 04, and we are unpacking the incredible evolution and the underlying mechanics of the link layer. If you've ever sat there and wondered how data actually travels across physical wires without turning into absolute chaotic garbage, you're in the exact right place.
So here's our game plan for today. We're going to start with the foundation of Ethernet. Take a peek inside an actual Ethernet frame, map out the CSMA/CD and exponential backoff traffic rules, and wrap up with Ethernet switching.
Section 1. The Foundation of Ethernet. From humble sketches to dominant technology. Take a look at this. It's Bob Metcalfe's actual original sketch of Ethernet from way back in 1973. It is honestly brilliant in its simplicity. It was designed to be cheap to deploy and built entirely around sharing a common medium, literally a thick coaxial cable that he dubbed the Ether. Every single station just tapped into this one shared wire. And you know, that core simplicity, that's a massive part of why it became the dominant standard. But what's really wild is how this tech scaled. I mean, we went from a humble 10 megabits per second back in the day to a mind-blowing 800 gigabits per second today. To put that in perspective, that's like upgrading from a horse and buggy straight to a supersonic jet. But here is the crazy part. The foundational logic of how it actually packages your data, it has remained surprisingly consistent. Which brings us to Section 2. Inside the Ethernet frame. Packaging the data for the journey.
You can think of the Ethernet frame like a super strict, highly structured digital envelope. Right at the very front, we have the preamble. That is 8 bytes, specifically ending in a 10101011 bit sequence. Now, this isn't actual payload data. It's literally a synchronized wake-up call to get the receiver's clock perfectly in sync. Next up, you've got your 6-byte destination and source hardware addresses, followed by the type field, which basically tells us what network layer protocol we are carrying, like IP, for example. Then comes your actual payload. Finally, at the very end is the CRC, the cyclic redundancy check. This is absolutely crucial. It's a mathematical error detection mechanism. If the receiver runs the math and the CRC doesn't match up, bam, the frame is instantly dropped. No second chances.
And let's talk about those addresses. We're talking about MAC addresses here, Layer 2 hardware addresses. And definitely don't confuse these with Layer 3 IP addresses. They are totally different beasts. A MAC address is exactly 6 bytes, or 48 bits, usually written out in hexadecimal. Here is how it works in practice. When your network interface card, your NIC, receives a frame off the wire, it meticulously checks that destination MAC. If the address matches its own physical burned-in address, or if it's the all-F's broadcast address, which basically means, hey, this is for everyone, it passes the payload up the chain. But if it doesn't match, the NIC just aggressively discards it. It doesn't even think twice.
All right, Section 3, Ethernet Medium Access, CSMA/CD. Establishing the traffic laws. So this begs a pretty massive question. What happens when multiple devices try to shove their digital envelopes down the exact same wire at the exact same time? Well, in the original Ethernet bus topology, where every laptop is connected to one shared line, you get what we call a single massive collision domain. Because it operated in half-duplex mode, meaning only one host can physically transmit at any given time, if 2 hosts tried to talk at once, their electrical signals would literally crash into each other on the wire and turn to garbage. We desperately needed traffic laws, and that's where our Medium Access Control Protocol comes in.
We call those traffic laws CSMA/CD. That stands for Carrier Sense Multiple Access with Collision Detection. It sounds like a mouthful, but honestly, just think of it like trying to have a polite group conversation in a pitch-black room. Step 1, you get your thought ready. You build your frame. Step 2, you listen to the room. You sense the channel. If it's completely quiet or idle, you go ahead and start talking. If you hear someone else, it's busy, so you politely wait. Step 3, if you manage to say your whole sentence without being interrupted, awesome, that's a success. But step 4 is the critical part. If you are talking and suddenly you hear someone else start talking over you, well, that's a collision. You both immediately stop, abort your transmission, and blast out a short jam signal. That jam signal basically yells, hey, the channel is corrupted, so everyone else on the wire knows to back off.
Moving on to Section 4. The binary exponential backoff algorithm, the mathematical solution to traffic jams. Okay, so you've just aborted a collision. Who gets to speak next? If both hosts just immediately retry, well, they're just going to crash into each other again, right? We need a mathematical tiebreaker, and that is the binary exponential backoff algorithm. Let's break down the math. After a collision, let's call it the mth collision, a host picks a random number, let's call it k, and it picks k from a range of 0 to 2 to the power of m minus 1. So after your very first collision, you randomly pick a 0 or a 1. But let's say you randomly pick the same number and collide again. The range expands. Now you're picking from 0, 1, 2, or 3. This exponential growth keeps happening until it caps out at 10 collisions, giving you a massive pool of numbers all the way up to 1,023. It dynamically stretches out the wait times, dramatically lowering the statistical odds that two hosts will pick the exact same retry time again. It is incredibly smart.
But what do the hosts actually do with that random number k? Well, they multiply it by exactly 512 bit times. And that specific calculation dictates the precise amount of time they have to sit and wait before they can go back to step 2 and try sensing the channel again. It's a beautifully elegant way for the network to dynamically adjust its own pacing when traffic gets heavy.
Section 5. Ethernet switching, upgrading from hubs to switches. Now, using math to manage collisions is great and all, but you know what's better? Not having collisions at all. By the 1990s, our networks were growing so fast that the chaotic collisions of the old bus topology just became totally unmanageable. We had to upgrade. We moved to a star topology, which introduced Ethernet switching. And you absolutely need to understand the difference between the early hubs and modern switches. A hub is passive. It's essentially just a dumb repeater. All connected links act as one single segment, meaning it's still one massive collision domain. It's like a chaotic, unregulated four-way intersection. But an active Layer 2 switch, total game changer. It takes an active role. It stores and forwards the Ethernet frames. With a switch, every single spoke connected to it is its own completely isolated Ethernet segment.
Check out this topology. With an active switch sitting right there in the center, every single spoke becomes an independent collision domain. This means a frame sent from host A over to host B doesn't crash into a frame being sent between host C and host D. The switch acts almost like a multi-lane highway overpass. Traffic just flows over and under each other without interacting, which means we can finally have simultaneous transmissions without the chaos.
And these active switches are incredibly smart. They don't just blindly blast your data out of every port. They actively build what's called a dynamic forwarding table. When a frame comes in, the switch peeks at the source MAC address to learn exactly which port that device is living on. Then it looks at the destination MAC to selectively forward the frame only out of the specific link it needs to go down. Now, if it hasn't learned where the destination is yet, it will temporarily flood the frame out of all ports just to be safe. But this self-learning mechanism is what makes modern switches entirely plug and play. You just plug it into the wall and it figures out the network all by itself.
All right, Section 6, Summary and Key Concepts, Looking Ahead.
Let's bring it all together. You should now have a really solid grip on these core mechanics. We've seen how Ethernet evolved from that shared, chaotic bus into modern switched topologies. You know that 48-bit MAC addresses physically route our payloads. We broke down the polite conversation rules of CSMA/CD and the mathematical brilliance of the binary exponential backoff algorithm that statistically resolves our traffic jams. And finally, we saw how modern active switches completely isolate those collision domains via their address learning capabilities. But of course, that leaves us with a pretty fascinating puzzle for our next explainer. Think about this. If physical switches solved the physical collision problem on a wire, how on earth do we tackle logical isolation using virtual LANs? And maybe even more mind-bending, how do we manage medium access and collisions when our wire is literally just thin air? You're definitely going to want to keep today's concepts fresh because you will absolutely need them when we tackle VLANs and wireless LANs. Thank you so much for learning with me today, and I'll catch you in the next one.